Hey everyone, and welcome. If you are an IGCSE Physics student, I am so incredibly excited to guide you through this explainer on wave diffraction. If you've ever been sitting there staring at those ripple tank diagrams and wondering exactly what the examiners actually want to see, well, you're in the perfect place. Today, we're not just going to memorize what diffraction is, we are going to completely master the spatial mechanics and the exact nitty-gritty nuances of spreading waves that your exam questions revolve around.
But right off the bat, I want to hook you with a little everyday mystery. Think about this. Why is it that you can clearly hear your family talking in the next room, maybe even through just a slightly cracked door, but you absolutely cannot see them? It just seems like a normal fact of life, right? But physics holds the exact answer to this. And by the end of this explainer, you're going to know precisely why this happens.
Okay, here's our quick roadmap for today. We'll start with the phenomenon of diffraction, then look at constants and changing variables, dive into gap size versus wavelength, compare sound versus light waves, and finally, wrap up with how to draw the perfect diagram. All right, let's dive into part 1, the phenomenon of diffraction, or the spreading of waves.
So this definition right here, this is your absolute bread and butter. Diffraction is the spreading out of waves as they pass through a gap or move around an obstacle. I really want you to mentally highlight this exact phrasing. Seriously, lock it in, because this is precisely the wording examiners are hunting for when they ask you to define the term. It's all about that spatial spreading.
Let's look a bit closer at how waves actually behave when they slam into a single edge or a barrier. It's kind of neat because not all of the wave is affected. The bulk of the wavefront, the part that completely misses the barrier, just keeps cruising straight ahead on its normal path. But the part of the wavefront that actually scrapes that edge acts as a bending point. The wave literally reaches around and actively bends to fill the empty space behind the barrier, creating what we call the shadow region. And here is a huge rule to remember for later. You get a much greater bend into that shadow region when the wave's wavelength is large relative to the size of the edge.
Moving right along to section 2, constants and changing variables. Let's look at what alters and what survives.
Now this is a crucial dichotomy for your exams. You've got to understand the strict split between variables and constants. Take a mental screenshot right now. The variables, meaning the things that actually change, are direction and amplitude. The direction spreads out angularly into new territory, and because all that energy is now being stretched over a much wider area, the amplitude and intensity start to fade. But look at the constants over there. What survives? Well, the speed remains completely unchanged, the frequency remains completely unchanged, and absolutely crucially, the wavelength remains unchanged.
To sum that up beautifully, just remember this. Diffraction alters the wave's path and intensity, never its fundamental properties. Keep that in your back pocket. The true core identity of the wave, its speed, its frequency, and its wavelength, always survives the bending process.
So looking at the anatomy of intensity, we see that the energy isn't just handed out evenly. The highest intensity, meaning the greatest wave amplitude, is always right there at the absolute center. We call this the central maxima. As that wave energy spreads sideways from the center, you get these fading edges. The amplitude just gradually decreases the further out you go. Okay, on to section 3, gap size versus wavelength. Time for the mathematical relationship.
Now, what's really fascinating here is the mathematical ratio between the gap size, which we refer to as d in physics, and the wave itself. To get maximum diffraction, meaning the absolute greatest spreading effect, your gap size must be approximately equal to your wavelength. We write this as d is approximately equal to lambda. On the flip side, if you're seeing minimal diffraction, where there's little to no spreading at all, it's because the gap size is way bigger than the wavelength. I really need you to internalize this absolute rule. To force a wave to diffract significantly, the gap must be comparable to, or even smaller than, the wave's own wavelength. If the gap is just massive compared to the wave, well, the wave just sails straight through without bending, like the walls aren't even there.
Section 4, Sound versus Light Waves. It is time to solve our real-world mystery.
Let's walk through this real quick. Remember our question? Why you can hear someone but not see them? Just look at the wavelengths. Sound and radio waves have a low frequency and a very large wavelength, and because their wavelength is so large, they easily meet that d approximately equals lambda rule for everyday objects. A standard doorway? That's actually the perfect gap size to cause maximum diffraction for a sound wave, allowing it to easily bend right around the corner and into your ear. But light waves and microwaves, they have incredibly high frequencies and extremely short wavelengths. Because their wavelengths are just so tiny, they have minimal diffraction ability in our everyday world. They only diffract through microscopic gaps, which is exactly why everyday objects cast sharp shadows and require a direct line of sight. The light wave is just too small to bend around the doorway.
Finally, Section 5, Drawing the Perfect Diagram. This is your exam packer's guide. Okay, when you inevitably get asked to draw a ripple tank diffraction pattern, follow these exact 5 steps to guarantee those full marks. Step 1, smooth curves. Draw a nice, continuous, semicircular curved edges spreading evenly from the gap. Step 2, constant spacing. Your wavelength must be perfectly identical before and after the barrier. Do not mess that up. Step 3, gap proportion. Make sure the physical gap you draw roughly matches your drawn wavelength to prove you understand maximum diffraction. Step 4, fading amplitude. Now, if you really want to flex on the examiner, deliberately draw your outer wavefront lines thinner or lighter to show that decreasing intensity we talked about earlier. And step 5, shadow infill. Ensure those curved waves spread outward, actively bending behind the barrier walls into the shadow region.
Seriously, guys, if you only take one single thing away from this diagram section, let it be the IGCSE golden rule. Always protect the wavelength spacing before and after the barrier. Don't just eyeball it. The absolute #1 mistake students make under pressure is drawing the waves getting closer together or further apart after they pass the gap. Remember the constants. Wavelength survives. Pick up a physical ruler in your exam, measure the distance between the lines before the gap, and use that exact same measurement for your curves after the gap.
All right, so we've covered the mechanics, the math, and the drawing techniques. But before we officially wrap up this explainer, I want to leave you with a final provocative thought, just to test how deeply you really get this relationship. Think very carefully about the constants and the variables we discussed. If you double the size of a gap in a ripple tank, what must you do to the wave frequency to maintain maximum diffraction? I'll let you chew on that one. Thanks so much for learning with me today, and keep exploring the amazing mechanics of our universe.